Woo, we are going ham on these applications, as you young folks say. I taught Mr. Kalis that one, going ham. He's using it now in school, so that's pretty exciting. So a little bit different though with applications for this one. Normally we're focused so much on, oh, we're going to graph it, we're going to find these numbers, minimum, maximum, whatever. But we're going to focus more on like what do they actually mean. So our learning target here is be able to relate the algebraic representation of a function to the context of the problem, and that is exciting, Jenny, isn't it, Jenny? Yes, it is. All righty. Well, without further ado, let's hop to it. Given a cost function, c of x, which returns the total cost in dollars of producing x items, the average cost function, c bar, equals c of x over x computes the cost in dollars per item when x items are produced. Hefty sentence there. Suppose the cost C in dollars to produce X Portaboy game systems for a local retailer is C of X equals 80X plus 150 for X being greater than 0, greater than or equal to 0, meaning either we're producing no games or at least a positive number of game systems, right? We're not going to talk about negative numbers. All right. Look at that. First little interpretation there. So in the context of this problem, what is the input for C of X? Well, my input is my X value. We know that the input is going to be the number of Portaboy game systems produced. I like it. Cool. So let's jot that down. Let me get a marker ready here. Number and we continue. Figured I'd pause, write it down, save a little time. So number of Portaboy game systems produced. In the context of this problem, part B, what is the output for C of X? Well, that would be the total cost of producing X number of game systems, right? So if I put in a 1 game system, I will get $230 to produce it. If I do 2, that'll be this, 3, this, so on and so forth. So let's jot that down. Boom, there we go. Total number or total cost of producing X game systems. X being some number, some positive number or equal to 0, right? X is greater than or equal to 0. All right, part C. In the context of the problem, what does C bar of X represent? Well, I think we actually already talked about that in this whole, when we were reading the problem, is that that's going to be the average cost of producing X number of game systems. Excellent. So as we produce more and more and more, the average cost of producing each game system is going to decrease, right? We're going to explore more of that in a little bit. Next part, the solution to the inequality C bar is less than 100, is the interval 7.5 comma infinity, unbounded. Interpret the meaning of this solution in the context of the problem. Okay, well, what the heck does this mean? I'm gonna pop up a graph real quick. So I got Desmos up here. Love me some Desmos. This red graph, that's our average cost function, which I have typed in there. And then the y equals 100, that's what we were talking about there. We said where C bar was less than 100. Well, what's happening right at this point here? Oh, it's 7.5. So we said in that open interval, 7.5 comma infinity, it's less than 100. Well, what does that mean here? That means once we produce over the 7.5 units, our cost is going to be below $100. Bada boom, bada bang, there we go. The average cost of producing each game system is less than $100 when more than 7.5 systems are produced. As you can see right now, guys, a lot less math than we're used to in this dope math lesson. Brought to us by the one and only Mr. Kalis. He's the mastermind behind this, and I'm pretty excited about it. I'm pretty excited. All right. In determining the behavior of C bar as x approaches infinity, Jackie found that as x approaches infinity, C bar approaches 80. Cool. Interpret Jackie's result in the context of the problem. So what does that mean exactly? As our function goes to infinity, we're approaching 80. So if I bring Desmos back up there we are. So I've got my red C bar function. And then that green line, that's the 80 that was referenced in there, right? It's approaching 80. Well, what is that exactly? Well, we might remember that as a horizontal asymptote of this rational function. Okay, so but what does that mean exactly? So what that's saying here is that for some very large numbers of x, like as we approach or as we're producing more and more and more and more systems, the cost is getting increasingly closer to being $80 per system to produce, almost getting there, but never quite, right? But as we go up, it's getting cheaper and cheaper and cheaper, but only to an extent, right? It's approaching $80 per system to produce these things as we produce more and more and more systems. And there we have it. For large numbers of systems produced, as the number of systems increases, the average cost of each system gets closer to $80. The more you make, cheaper it gets. I like it. In bulk. Like Costco, you know? Duh. Costco has a plan too, you know what I'm saying? Get that stuff in bulk. Alrighty. Part F. Use your calculator or another graphing device, perfect, we already got one, to graph C bar of x in an appropriate window. Sketch the graph here and mark with coordinates the point on the graph where C bar of x equals 95. All right, so we have our Desmos graph. So here we are on Desmos, and remember we said we're not really worried about those negative x values. We're really only worried about the positives. So I'm going to adjust this window to be something like this. If you run your TI-84, I'd say go anywhere from 0 maybe to 150 up here, and we can go all the way over to, you know, maybe 100, 150, get a nice little square looking view. Awesome. And then we said the point was where C bar of x is equal to 95. So when does it equal 95? We got to be somewhere close in here. And looks like we're going to be right at 10. There it is. Whoop, we saw it. I think we saw it. I'm going to try and get it up there. I had it. And then there it is. All right. So 10, 95. We're going to want to notate that. We've got our asymptote there. I made it a dash line. It turned purple. All righty. Let's sketch this out on our notes while I continue to move it. There it is. Woo! All right. So we got our graph coming along here. I'm going to jot down my asymptote. Lovely. And then my graph, why don't we go with the graph? I'm going to change up colors. I'm going to go with a little dark blue. I think dark blue would look lovely here. So I've got something like this. There we go. There we go. And at this point, we have 10, 95. I think that's pretty much what we need there. Maybe I'll label this guy as our C bar of x. That's our function right there. I love it. I got my, I'm going to throw my arrows on my axes. This is my y. This is my x. Beautiful. Or I guess we could call this just our, yeah. There we go. I like it. Now, let's see here. The next question says, what does the ordered pair you marked in part F represent? Like, yeah, I can mark an ordered pair, but what the heck does that what does that represent? Can we put that into words? So let's think about our input, output, all that stuff we've been talking about early on in parts A and B. Well, when my input is my x, right, and that's the number of systems, and then the output was my cost of that system. And then once I divided everything by x, the number of systems produced, that's when we got our average cost function, the C bar of x. So my input is 10, and then my output of the C bar of x function is 95, meaning when I produced 10 systems, my average cost to produce each system was $95. All right, there it is. Let's put it down in writing. There we have it, ladies and gentlemen. We got when 10 systems are produced, the average cost to produce each system is $95. That's awesome. That's it for this problem. We're going to go on to another one. Jenny, how you feeling? She's exhausted by this. She doesn't usually have to deal with average cost functions, you know, but we're here doing it. Jenny's here. She's just along for the ride. Let's keep it moving. Let's keep grooving. Whew. Now we got ourselves a marketing problem. So when successful new software is first introduced, the weekly sales generally increase rapidly for a period of time and then begin to decrease. It's kind of like when they release like a new game or something like that, right? Everyone's like, I got to have it. And then it kind of peters out. Suppose that the weekly sales S in thousands of units, T weeks after the software is introduced, is given by that function. S of T equals 200T over the quantity t squared plus 100. Label the graph with the variable names for the axes. All right. Nice. All right, let's hop to it. We got those nice little boxes there. Fill them in. So for what will be my y-axis, it'll be our sales, S, in thousands. Cool. And then how about our x-axis? Well, that'd be our weeks, T, after the software is introduced. Beautiful. Wonderful. Fantastic. I like it. Part 1 done. Good stuff. So we often label our axes with different letters to notate what we're talking about. S for sales, T for time. I like it. Write an algebraic inequality whose solutions answer the question. When will sales be 8,000 units per week or more? Now I'm going to switch up colors before I forget because I feel like using the same color all the time can get a little boring. All right, so my sales S of T is 200 T over T squared plus 100, and I want that to be 8,000 units per week or more. So I would say it's greater than or equal to just 8. Remember, because these are in thousands of units to begin with. Got to be careful there, right? Whew, that could have been bad. So not 8,000, but just 8. Excellent. Mark the graph with an appropriate interval representing the solution to the inequality from part B. So what we're talking about here, and since the graph is green, I'll use a different color. I'm going to go with this blue color here. 8 would be roughly around this area. That's actually a little hard to see there. I'll change colors again. Go with a bright pink. So right here. And then where else is it going to be? It's going to be hitting right around there, right? So we got 8. Sorry, 8 is right up here. So I'll even mark that as an 8. And then there we go. So that would be the area representing the solution to part B. Okay? Beautiful, fantastic. I got that horizontal line to reference it. Whoa, that went off track there. So I'm just talking about up there. Let's continue. So in the context of the problem, what is the input for the function S of T? Well, that would be my T. That would be the number of weeks after the software is introduced. There we go. Number of weeks since the software is introduced. How about the in the context of the problem, what does S of T represent? Well, that would be our number of sales in thousands of the software. There we have it. And if you guys need to, pause it to write some of these down. I know there's a lot of writing, so that's why I'm doing the pause and write to save a little bit of time on the video. But if you need to pause, feel free so you can jot these things down. I know they can be kind of tricky and wordy. All right, part F, and then uno mas. The solution to the inequality S of T less than 3 is 0 to 1.535 union 65.131 to infinity. Interpret the meaning of this solution in the context of the problem. So what is that saying? Well, S of T is less than 3. And I know that S of T is the number of sales in thousands of new software. I just did that in part E. So what this is saying is that sales are less than 3,000, and it's occurring from 0 weeks to 1.5-ish weeks, and then at 65 weeks on. Roughly 65. We'll use the actual numbers in our answer. But there we go. So we're just saying this is the time frame of when sales are going to be less than 3,000. And as we know, as the software has been out for a while, it just kind of slowly peters out, as we said earlier, to nobody really wants it anymore. All right. So let's write that one up. So I found this one was a little bit tricky to word. So the sales are less than 3,000 from when the software launches and before 1.535 weeks have passed, because we're not including that like when it hits 3,000, because we want to just be less than 3,000. And also after 65.131 weeks have passed, right? We're not including that number because we don't want to include the 3,000. Awesome. And there's other ways you can word this one using a little bit more with the math context, with like greater than or less than. But this is how I decided to word it. So this last part here, the graph of S of t as a horizontal asymptote. Determine the equation of the horizontal asymptote and interpret its meaning in the context of the problem. All right, well, let's look back at our function here. We have S of t is equal to, in case you lost it, 200t over t squared plus 100. So the degree of the numerator is smaller than the degree of the denominator, which means I'm going to have a horizontal asymptote of y equals 0. Since we labeled our asymptotes s and t, I'm going to go with s of t is equal to 0 is my horizontal asymptote. More importantly, what does that mean in the context of this problem? Well, that means as time goes on, what are our sales approaching? 0. Nobody's buying Windows 95 anymore. Or maybe one person did, which is why it never gets to 0, right? Maybe some dude's like, hey, man, I want that Windows 95 back. When they purchase it, they find it somewhere, so somebody bought it. So it's never really approaching 0 sales. Get what I'm saying there? All right, let's jot that down in a formal way. And there we have it, folks. As the number of weeks gets larger, the number of sales gets closer to 0. I think that's clear and concise. One last example. Thank you guys for hanging in here. I'm having a blast with these wonderful problems here. And, of course, once again, Jenny's having a blast over there. She's falling asleep in class again. But, hey, no worries. There's math to be done. We're occupied. Let's keep moving. All right. I'm excited about this problem here. Mr. Kalis did this. Put me in the problem. Mr. Allen recently started a new band, Mr. Allen's Money Train. It's a dope name. In performance, the band wants to release 20,000 cubic centimeters of confetti from his favorite supplier, Fetty Wap. He actually has a company called Confetti Wap. See what I did there? It's good. All right. To hold this volume of confetti, they want to build a box with a lid this time. We don't want this stuff blowing all around. No more open top box. Sorry, G-Eazy. Can't be using your open top box that are so easy to open. With a square base and rectangular sides. Now, wanting to paint the box in solid gold, they want to minimize the surface area of the box. Solid gold, not gold paint. We're using actual gold here, so we got to keep costs down, you know? All right, write the equation for a function that gives the surface area, SA, surface area, in square centimeters in terms of the length, x, in centimeters, of each side of the square base. Okay. Woo. Woo. Well, let's first talk about our surface area, shall we? I'm going to go orange. So the surface area of this thing is going to be, let's see here, 2 bases, and we're going to have 4 sides, right? 2 bases, 4 sides. Well, my bases are x squared, x times x, so that would be 2x squared. And my sides are all x by y, so x times y, but there's 4 of them, 4xy. You dig? I dig. Okay. Now, I do know that the volume, right? The volume is going to be 20,000 cubic centimeters. So perhaps we could use that to our advantage. So volume, I'm going to go right here. Actually, I'm going to go over here. Got all this space. I don't even know what to do. So my volume is going to be x times y, right? So x squared y. And I know that my volume is 20,000. So I can actually solve for y here and then substitute in so that I can get my function in terms of x as it asks. All right, so I'll divide by x squared. So I get y equals 20,000 over x squared. Beautiful. Fantastic. I'm going to substitute that in to my surface area function. So now I will have s surface area of x. You know what? I can do surface area of x. That was a funky x there. Is equal to, I've got 2x squared plus 4x And then in place of y will be the 20,000 over x squared. I like it. Awesome. Fantastic. So let's do a little bit of simplifying. We don't have to plug into our calculator, but I feel like it's a little unsightly with, I know that things can be taken care of here. So I'm going to have 2x squared, and then when I multiply in, the x's will reduce, and I'll get 80,000 over x. I like it. That's good stuff. Fantastic. It's a clean looking equation now. Do you think we can even clean it up more? Do you think we can get this all into one fraction here? I think we can get a common denominator. 2x squared, if I put that over x, I need to be 2x cubed. So let's go with the final one here. Oh, this is going to be beautiful. This is going to be beautiful. I'm going to have 2x cubed plus 80,000 all over x. They all wanted to hang out. Everybody wanted to be in the same fraction there, right? That's fantastic stuff right there. I'm good with that. I hope you're good with that. Let's keep going. What surface area results if each side of the square base is chosen to be 10 centimeters? Well, I mean, you could go back to the drawing board here and be 10, 10, and then, then I got to figure out what y is. Well, we just made a fantastic function here, surface area function. Let's just substitute 10 in. So if I do substitute 10 in to this function, throw it in my calculator, I will have, bing bong, zoop, bam, and I get 8,200. That's a 2 zeros there. I don't want that. 8,200 centimeters, and we're talking surface area squared. Nice. Like that. There we go. Next one. Are we going to get a challenge here? Are we going to get a challenge finally? Part C. Consider the inequality surface area as a function of x is less than 50,000. In the context of the problem, what do the solutions to the inequality represent? We're not asking you to solve it here, right? We're not asking for the answers. Well, I mean, numerically. What we're saying is, what do the solutions represent in this inequality? So if I were to solve it, I would get some x values for when the surface area is less than 50,000. Well, what are those x values? Those are the lengths of the base. So there we go. There we have it. That's what it represents. Formally written down, the length of each side of the square base for which the surface area is less than 50,000 centimeters squared. All right. What dimensions of the box minimize the surface area? So now we want to actually minimize the surface area here. So to save a little bit of time, I'm going to draw a sketch of the graph. Since we've done a few of these here. Actually, you know what? Let's get in that TI-84. All right, so I've got my function plugged into that nice, beautiful, cleaned up function. I set my window accordingly. Feel free to pause and adjust your window as well if you'd like. Let's head to the graph. Boom. There it is. Wonderful. We wanted to minimize the surface area, so let's go ahead and calculate that minimum. Left bound. Right bound. And we'll guess. And we've got 27.144 and 4,420.838 rounded. All right. So what are my dimensions to minimize the surface area? Well, the x, so the x is my base dimension. That y is not my height. That is my surface area function value. That's the actual surface area, 4,420. Okay, so that means that one of the dimensions is going to be 27.144 centimeters by, and the other one's going to be 27.144 centimeters by, and then how do I find the last one? Well, if I plug that into my trusty y equals 20,000 divided by x squared, So y equals 20,000 divided by this number squared, then I'm actually going to get 27.144. This is going to be a cube, 3 dimensions. Cool. Awesome. I like it. There we go. Last couple. Suppose that that the gold paint used to paint the box is $50 per vial, and that each vial covers 100 centimeters squared. Assuming the band chooses to make the box with the least surface area, how much should the band expect to pay for the paint? Well, lucky for us, we've got our graph still up here. Remember that y value we talked about? That is our minimum surface area. So if I were to take the 4,420.8378, divide that by 100, remember, move your decimal place, whoop, whoop, 44.208, that would give me the number of vials, right? I divided by 100 because each one covers 100 centimeters squared. So that's my number of vials. Number of vials. And then, well, how much does each one cost? $50. So if I take 50 and multiply it by the 44.208, well, hold up here for a sec. I don't think I can order 44.208 vials, right? So really, I'm going to be doing 50 times 45 vials. We're going to have a little gold paint left over. Maybe we'll touch something up later. Always good to have a little touch-up paint. So if I multiply those together, it's going to be a cost of $2,250. That was dragging me. That was kind of fun, though. Boom. Lovely. That's part E. I know this is getting a little long, but I appreciate you guys staying along here. So what happens to the surface area as x approaches infinity? Well, as x approaches infinity, we can see our graph is going way up there, right? So as my surface area is going to go to infinity. Lovely. So as x approaches infinity, I'll write out the full statement. Surface area approaches infinity. Cool. And the last one. What happens to the height of the box as x approaches infinity? Well, remember we have that height equation, y equals, what was it, 20,000 over x squared. So as x approaches infinity, as x gets infinitely large, we have ourselves a horizontal asymptote there of y equals 0, so it's going to be approaching 0, right? As this number gets bigger, it's going to be a fixed number of 20,000 divided by an infinitely larger number. It's going to go to 0. So as x approaches infinity, the height approaches 0. I like it. That was fun. That was an intense bit of problems there. I appreciate you guys sticking around there. I know it got a little bit lengthy. I can see the timer, 28:08. I better stop. But first, River Dog Jenny, make sure you follow her on the gram if you don't already. You guys have a great day. America, freedom, rock and roll. Costco, Fetty Wap, invest in Confetti Wap. I want one day for him to actually sell Confetti Wap. All right, have a great day, guys.